Alright, time for another draftphysics.com, debatephysics.com also, video presentation. On the subject of temperature, so this was in my recommended videos, MarbleScience. I don't think I've watched any videos from this channel before, so we'll see what else they has. He's going to talk about temperature and the fact that somehow we don't know what temperature is, and people have all kinds of answers, and I will just say for my part that it's always been seeing it as little stuff moving, that's all. You know, that you could understand the ground is made out of sand, let's say, and you hit it and the little bits of sand start moving, okay, and then they don't stop moving until they're dissipated all their motion into all the grains of sand in a way or something, and so then you don't even see the motion because it's so subtle. But basically it's just movement. So heat was movement. Now, after doing all these physics videos, I'd argue that it's just a form of momentum. It's just masses moving. In this case, they're very small masses, and in this case, it's not movement in necessarily a straight line. So it's movement in that way, that way, that way, all kinds of different kinds of motion, and basically just creating a pressure that transfers from atom to atom to atom to atom. Realistically, I guess we should say from electron to electron to electron to electron. And that's all it really is. You're just pushing electrons into electrons. The surface of atoms are electrons. You're pushing the electrons into the electrons. It's just motion, moving through a very dense, the apple is to the earth what the atom is to the apple. So it's a lot of atoms that have to be jiggled for the heat to move through the apple, so to speak. But it's just momentum. All motion is momentum.
Explain to me, like I'm 5, what is temperature? Is one of the most difficult questions you can ask a scientist.
So I don't think so. It's really not compared to earwax, I don't know, those little things you get in your eyeball.
And typically all you get are stories and analogies, but
yes, analogies are really great, frankly. So I think my sand analogy isn't bad. You could even think of sticky sand, or you can think of lots of ways to make it into a medium, and the fact that it just moves through it like sound or some other thing. You could just compare it to sound and just say, yeah, sound is a kind of heat. It's a weak heat, but it's heat. It's motion in the atomic structure.
not actually a straight answer to what temperature actually is.
The amount of motion. No motion, no temperature, motion, temperature. It just means you have some momentum. So it's like a fish standing still and its fins are still moving. Atoms and molecules can be stationary, but they can be doing a lot of this.
And isn't that astonishing? It's such an everyday quantity, and yet it is so difficult to explain.
Yeah, I don't think it is that. Like I said, it's just motion, 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 motion. Clearly motion, because it transfers as motion. It moves from place to place. Heat moves. Kind of obviously it's motion.
I sure struggled while making this video, but I'm really happy with the result, and I prepared some beautiful simulation models for you.
Oakley doke. They're all the same color.
And I structured this video into 3 levels, so we will start nice and easy and we will gradually approach the more complicated aspects.
Alright, well, felt temperature, this isn't going to be too interesting, is it? No, I don't think so.
Every child knows that temperature tells you how warm something is, but then again, what does warm even mean? It's a bit...
Yeah, let's see, I mean, talking about how a neuron, gives you a signal for something cold and something hot, and then often you can confuse those neurons, obviously. So you can, dip something in cold water and then put it in hot water and they'll think it's colder even, that kind of thing.
like telling someone that velocity measures how fast something is.
Yeah, and that's partly to do with temperature, is speed. So you know that in certain conditions you can increase temperature just by increasing speed.
It's just replacing one word with another. Of course, we have a sense for how warm something is when we touch it, but how something feels is very subjective and does not really make for a good definition.
No, this is, this isn't science. This is something else. I mean, we know that our body senses, and it has a thermometer of sorts, and it's pretty crude and uninteresting. I mean, frankly.
And furthermore, there are factors other than temperature that influence our thermal sensation.
Right, so what's the use? Why talk about it? We know that we can measure it exactly, temperature. We don't have to measure it fudgily. We don't have to feel it. We can measure it.
For example, if we place these two objects next to each other, over time we expect them to equilibrate to the same temperature.
Right, but one of them will absorb your temperature much quicker, so it will feel colder because it will absorb your temperature. So, again, not interesting.
That's an important aspect of temperature that will also be important later.
So the movement of temperature is a different subject than temperature itself. And obviously, it always, like everything else, it moves from high to low, high pressure to low pressure. That's the tendency. Pretty strict tendency.
Still, after hours of sitting next to each other on my desk, this piece of metal feels quite cold, and this piece of wood feels quite warm. How is that possible? It's because these two materials have a very different thermal conductivity, which, additionally to the temperature, also has a large influence on our thermal sensation.
So again, this really doesn't explain what temperature is. What does it look like inside an atom or inside a material?
All in all, seeing temperature as how warm something feels is usually enough for our daily life, but it doesn't really bring us closer to understanding what temperature actually is from a physical perspective.
So it's obviously that a heavy metal will do a lot of things based on its density. It'll sink faster, it'll do lots of things because it's more densely packed with electrons and protons. So, and one of the things it'll do is that when it's holding temperature, it has more temperature it can hold, because it has more little bits to move around. Kind of obviously. So obviously you're touching something with a higher density, which means it can pull, or it can give you, or it can take energy much more quickly. It's a higher amperage, you could argue. It's a thicker wire.
Jack Chitterelli?
Oh crap. Yeah, you have to download everybody's videos nowadays. Alright, he says, to get a better understanding.
Wouldn't it be great if we could, see with our own eyes what happens in the material on the atomistic level when we change?
Exactly. So yeah, let's just talk about what happens. And what happens is stuff moves, and it moves faster the hotter it gets. It's just not much more complicated than that. It has more momentum.
Sure. Experimentally, that's not so easy, but there are computer simulations that mimic the behavior of atoms, and these are amazing to get an intuition about such.
Well, you only think they're amazing if you think they're accurate, so that's the tricky part.
Atomistic processes.
But, there's lots of other mechanisms. I mean, people have, machines that just bounce the little ball bearings and blah, blah, blah. And the faster you bounce them, they have higher pressure, so it shows the difference between, low temperature and low pressure, high temperature, high pressure.
Here you can see a simulation of a bunch of argon atoms. I chose argon because, as one of the noble gases, it does not tend to form any chemical bonds, which is great to keep things simple.
So, but the problem with that analogy is that there's no reason for them to clump. They would just dissipate. So it's not going to be very useful if you did it honestly. So you really should have created some sort of reason, like in a bubble or some other mechanism to contain the atoms.
Currently, the system has a temperature of 85 Kelvin. That's pretty cold, minus 188 Celsius.
So it's obviously not kind of cold because it's kind of hot. so there's no point in us making, the human scale, the definition of hot and cold is what we feel comfortable in. Obviously, it means there's motion, and it's this much motion. And I would say that, obviously, if I put that temperature constantly on a surface, and I kept applying it into a surface that was like the size of the Earth, if it goes and concentrates in the center, because I'm pushing it from both sides, you could argue that it could end up being 4,000 degrees in the center of the Earth. Pretty much what the Earth is doing right now, frankly.
So cold that argon, which is a gas at room temperature, is mostly liquid. We can see that in this liquid state, the atoms move around, change their positions, but still mainly stay in this little droplet. Let's see what...
Alright, so I doubt that that's what it would do if you put it on a slide or something in air pressure. But whatever, let's continue, see what happens.
What happens if we cool the system down further? As you can see, there's less and less movement. At some point, the atoms are still shaking a little, but they are no longer moving freely across the entire droplet. The argon is now frozen. It's in a solid state.
Alright, so I would compare this, as I compare other things, to a school of fish. And you can understand that there can be a school of fish where most of the fish are just flying in all kinds of directions. But it has a net movement. So the whole school, even though it's swirling and doing all kinds of weird shit, ends up going somewhere. Now you could argue that there's a temperature to the school. Okay, and then there's also the temperature of its net motion. They're both essentially temperature. You could argue that a laser beam is just temperature going the same way. It's just momentum going the same way. It's electrons and protons moving. They all move the same way. Then it's a force that we like to play with. This isn't a force we can play with. But if I made all that motion in one direction, then we'd call it momentum. But it's momentum now.
If we decrease the temperature even further, there's even less movement, which also means that there's less energy in the system, less kinetic energy of the atoms.
Alright, so there's no kinetic energy, so it's just no such thing. There's just momentum. There's mv, there's masses moving, there's no v squared function.
If we instead increase the temperature, the movement is increased, and with that also the kinetic energy in the system is increased.
So I don't know what the floaty things on the outside are. Obviously nothing's giving them any motion, yet they're speeding up. They can't be speeding up unless they make contact.
If we go all the way up to room temperature, we can see how the droplet quickly evaporates and the argon comes into the gas phase, the state that we expect for a noble gas at room temperature. What we can learn from observing the atoms at different temperatures is that...
So the temperature is being caused by something. Obviously the atoms don't hit each other in a realistic way. The electrons hit each other. They're banging into the increasing force that happens when you put two electrons close to each other. The force increases, the repelling force. And so it's that elastic spring that the things are hitting each other with. So there's no friction, there's no waste, there's just a bunch of perfectly elastic interactions. And ultimately all of that motion has to be dissipated by pushing on the force that is containing. And in the case of atmosphere, and that force would be a bunch of other molecules in the atmosphere that the stuff has to hit through. And then in space, where there's very few atoms and very little to hit, you're still contacting the actual photons that are flying at you from all directions. They hit you, okay, with a certain frequency, and depending on how hot you are, you reflect them with a tighter or looser frequency. That's how we tell temperature, by looking at something. Because the thing, when it's hot, changes the frequency of the photons.
Temperature appears to be correlated to the velocity of atoms, and with that to the energy of the system.
Well, whatever that means. Energy of the system is just kind of vague and meaningless, because the absolute energy is all the motion, and we can't do much with any of that motion.
And this can already provide some great intuition about what the effects of temperature are. For example, if you imagine you touch something very hot, then the violently shaking atoms of that hot material are banging against the atoms in your finger, which in turn makes the atoms in your finger start to shake vigorously. At some point, the atoms in your finger are bouncing around so violently that structures in your skin, like proteins and that kind of stuff, get ripped apart.
And you don't feel any of that, though. So, if people who've been burned, you feel it way after it already happened. So what you end up feeling is the fact that you've killed a big pile of their cells, and that the ones on the periphery that you didn't melt or burn or break, the neurons are sensing the fact that there's a bunch of tissue damage. And that's what you feel.
And destroyed. And that's how high temperatures can hurt your finger. But while understanding that temperature is
so it really doesn't hurt until after you've done the damage. So if you stick your hand in a candle flame, you're going to feel the damage it makes. You're not going to feel the temperature. But if you stand a few feet from a fire, you'll feel the radiant energy hitting you and heating the surface of your skin. So you're detecting an increase in temperature, but it's not an unpleasant sensation until you get really close.
Related to the velocity of atoms is very useful. It is still only something that is correlated to temperature. It's not really what temperature is. The velocity of atoms is a velocity, it's not a temperature.
So, yes, it is. It's perfectly proportional to the temperature. The velocity is the temperature. So, yes, every single atom, you could take its temperature by saying how fast, how much momentum does it have. But obviously what we do is we stick a thermometer in and we get the net temperature, the average temperature. So the average atom speed that it's hitting, that's what we get, is the average speed. That's the temperature. So it's perfectly proportional to the speed of the surface electrons, let's say. All right, take a little pause. All right, let's continue.
Really understand what temperature is, we have to dive into the statistical roots of temperature.
Okay, so really, this is just trying to say, well, we're going to avoid looking at it as what do individual atoms do, and then just say what's the net product. Well, it's kind of cheating the argument. So it's like a water wave. I've explained, water wave moves in one direction, but there's lots going on for it to do that. There's water molecules, they hit a higher pressure, and they are going to seek a lower pressure. So wherever the lower pressure is where they're going to go, the less heat, so to speak. So everything just moves to where there's less pressure, or you could say less heat, or less momentum. And so the water ends up going up into gravity because that's less. It takes less work to push the water up against gravity than it takes to push it into a non-compressible liquid. And certainly going down isn't going to work because you're not going to compress the ground. So there's a lot going on. And so saying, we're going to talk about statistics and the fact that there's a water wave, slowly but surely the pressure does push forward. But, it's very complicated, and that's why the water wave moves kind of slow, is because there's a lot of stuff happening at a much higher velocity than the wave itself is moving.
Mikey Sherrill.
Oh, poo. Damn it. Ugh, commercials. Yuck.
The best way to explore the statistical roots of temperature is with another simulation model, one that is even simpler than the simulation of argon atoms. But before we dive into the model, let's recap what...
So simpler is usually, kind of a trick word in some ways, just because if you go simpler than atoms, you end up with, a smaller particle, but many, many more of them. And now they have two features. They have electrons and protons, so you have positive and negative things interacting, things that are attracted and repelled.
we know so far. Apparently temperature seems to have something to do with the energy, at least in the case of kinetic energy.
Well, no, it doesn't have anything to do with kinetic energy. It has to do with momentum, the energy of Newton, Descartes, and Galileo. That energy.
I think that was pretty obvious in the previous simulation.
No, there was nothing obvious about any v squared. Square velocity? No, I'm afraid not. Cube of velocity? Sorry, makes no sense.
And in the very beginning, we briefly touched on the idea that two objects have the same temperature if they are in some sort of equilibrium with each other.
Yeah, so again, we're talking about momentum, because we're saying if the big atoms move slow, it's going to be the same thing as the small atoms moving fast. It's going to be the same impact energy. Therefore, it's going to have the same effect on an environment. It's going to transfer momentum, and that's all things can do is transfer momentum. They can't transfer anything else. Kinetic energy doesn't transfer between small things and big things. Momentum does.
That means we're looking for a quantity that has something to do with energy and that reaches the same value in all parts of the system when we approach equilibrium.
Right, so we could have a system made out of different molecules, so substances, where they have hydrogens and oxygens and nitrogens and carbons and even uranium or some other really heavy atom, and somehow the temperature for all of those objects will end up being fairly consistent, even though they're going to move at very different velocities, because it's momentum that controls the universe.
Okay, now to the model where we can find out what this quantity is, find out what temperature is.
Temperature is energy, it's force, and matter carries force. So it's sufficuses, the force, and it's boulders, the matter being pushed. 5 sufficuses pushing a big boulder, same thing as 2 sufficuses pushing a small boulder. Same velocity.
Imagine a few atoms arranged on grid positions. I like to think of them as tiny marbles. And let's assume that these marble atoms cannot move all over the place like their natural counterparts.
So obviously, to do this sticking thing, the electrons on one atom have to still see the protons inside the nucleus of the other atom. And they have a will, they're attracted, they're compelled by an absence of pressure, a low pressure. There's low pressure between the electron and the proton. There's high pressure between the electron and the electron. So it's a pressure balance. And there has to be a net capacity for the electrons to see a low pressure point somewhere on the surface of the other atom. And they're bonding. It's just not a very strong bond, let's say. But if it's steel or something, obviously the bonds will be very strong.
That all they can do is bounce up and down. Bouncing, or movement in general, is a form of energy.
Right, but okay, so obviously in any elastic spring or anything, if I have a non-friction environment, it'll just keep jiggling once you jiggle it until you interact with it. You have to have some other object interact with it and steal some of the motion. So that's all you're waiting for, is some environmental circumstance to interact with those vibrations. Now, I would argue that that's exactly what the energy hitting you does. The energy hits you with a frequency, and you compress that frequency and increase that frequency. The stuff leaving you leaves hotter. The force is more compressed than when they got here. And that's how you lose your energy to space, is that photons hit you and you blue shift them.
So to make our atoms bounce, we have to add energy to the system. Let's assume that for each unit of energy that we add to the system, we can put one atom into its bouncy state.
Right, so this is purely momentum. You could just argue you could do this purely by understanding it as momentum. You've applied a unit of force. The unit of force gives a proportional amount of energy to the object when the force is consumed by it or attached to it, carried by it. And now it can spread that force by the rules of momentum.
For simplicity, let's also assume that there is only one level of bouncing. Atoms can either bounce or not.
All right, well, then you're out of luck. This is not going to spread anywhere. You're not going to be able to dissipate the heat. And so heat doesn't work that way at all. Heat works by spreading it, getting colder and colder and colder as it spreads. It dissipates the heat into more objects at a much lower velocity. So they don't all bounce at the same speed. It's not the rule.
The law of energy conservation tells us that the total amount of energy must stay constant.
Total amount of momentum must stay constant. You can't create it, you can't destroy it. It's always in the system somewhere. You can follow every piece of energy. Technically, we could trace it through billions of years. The energy that just did this, it has a billions of year life. It was somewhere yesterday, it was somewhere the day before, it was somewhere the day before, and it's going to be somewhere tomorrow. Part of it's going to be in the atmosphere right now. I just heated the atmosphere. Part of it's going to dissipate into space. Part of it's going to hit the earth and heat the earth. It's always on the move. Movement's always on the move.
So once we have set up our system, the number of energy units must not change. But
so then you're only going to have 4 blinky things. If you make 4 things blink and they have to bounce at the same speed, then you're only going to have 4 things blinking.
nothing contradicts energy transfer between our marble atoms.
There you go, right.
Let's
so
assume that energy units are from time to time randomly transferred to neighboring atoms.
Right, so pretty boring, not really heat.
In which case one atom stops and another starts to bounce. Okay, so that's pretty much all we need to explore the mysteries of temperature.
Well, it's not even close, because the mysteries of temperature have to do with exchanges between objects of very different densities and masses. So you're going to have all kinds of different vibration levels. The electrons on the surface of a uranium atom are at a much higher pressure than the electrons on the surface of a hydrogen atom, and so they're going to bounce. They're going to oscillate at a much different speed.
For example, if we add a bunch of energy units to one side of the grid and let the system evolve for a while, we can see how the energy becomes
So this is sort of cheating the argument, because you never have a circumstance where you have a temperature and zero temperature. So it's a pretty poor example, actually. He should have had some of them vibrating at a slow speed and some of them vibrating at a high speed, and then watch the high speed migrate into the cold speed. The cold speed won't migrate into the high speed. It won't move into the high temperature. It won't move into the high pressure. And it'll be high pressure will move into low pressure. So this is a very bad analogy, frankly.
Distributed among the entire grid. That's exactly how we expect heat to behave, right?
Yes, that's exactly how we expect heat to behave in an impossible circumstance where you have a zero temperature substance and then introduce a temperature to one part of it. But that doesn't happen anywhere.
Essentially, by adding energy to one end, we have made one side warmer than the other. And just like we expect, over time, the heat becomes distributed more equally.
There's nothing... Oh, shit, another commercial. The distribution is just an inevitable product of the contact. So
Introducing the new Jeep Grand Wagoneer with room.
even if it was a poison or some other kind of thing, it's going to do exactly the same thing in the sense that every time it has contact, it spreads the virus, so to speak. And you end up with a 50-50 chance in the end of what's going to be where. And so, yeah, it ends up being a probability. And it ends up being a probability that the most common state will be a mixture of 50-50. And the least common state will be everything at one end. But it's really not very interesting. It really doesn't have much to do with what's the nature of the heat itself. The nature of the heat itself is a mass with a velocity. That's the nature of heat. That's the nature of a temperature, is movement of a material object, including movement of a photon.
For the whole family.
And room to make a family. That's right, this baby was named...
Temperature is kind of right in front of us now, but we still haven't figured it out completely just yet.
Whatever, it's a little pretentious. Pretentious alert, pretentious. He's got it all figured out.
To understand what temperature is, we have to understand why the system evolves like we just saw. And
okay, that's just silly. That's just contact. It's just the rules of contact. You're spreading it based on hitting it. And yeah, this is what's going to happen. You're going to share conditions.
Also, when it stops to evolve. In our model system, energy is transferred randomly. In principle, any outcome is possible. But if we repeated the simulation over and over, we would always get...
So this probability stuff has nothing to do with entropy. This just has to do with mixing substances. Mixing is not energy, and it's not the subject of temperature.
Similar results.
Temperature does not behave as random or any of that. It does explicitly move from hot to cold. It does move from low pressure from high pressure to low pressure.
Of energy essentially distributing more equally. The thing with such randomly evolving simulations is that most of the time they evolve towards the most likely state. And the most likely state is the one that has the most possibilities for how it can be realized.
So let's just understand, in his simulation there was only, whatever it was, 15 units. So you only had 15 units. You're just saying it's heads and tails. And so you're starting with the 15 tails, and you're saying, well, later I'm going to have 15 and they're going to be spread out. It's just, it really doesn't have anything to do with the nature of heat and its transmission.
Let me show you what I mean by cutting the system into two parts, and
So you could sort of understand it like electricity. You have a voltage to potential, 0, 5 volts, whatever, and it's always relative, right? The 0 is not really a 0. It's just a relatively 5 less. So it doesn't matter whether I'm using 25 and 20. It doesn't matter. 5, 0, 25, 20, same thing. And you're just saying, what's the electrons doing? Well, electrons have a velocity, and they're going to share that velocity, that pressure, with each atom. So when it shares, it's going to split what it has. So if it's 10 pounds overweight, it's going to make this atom 5 pounds overweight, and it's going to be 5 pounds overweight. And then this atom's going to share, and it's going to be 2.5 pounds overweight, and this one's going to be 2.5 pounds overweight. So it migrates progressively, and obviously as the pressure is high enough, it's going to keep increasing that pressure until everybody's the same fatness. The fatness of your potential on this side. Everything will end up 20 pounds overweight.
Again, add a bunch of energy units to one side. For the left part of the grid, there are a lot of possibilities the system can be in. Roughly 5.5 billion combinations of different...
And again, it has nothing to do with heat. It's always the same temperature. It's never any other temperature. So what does this have to do with temperature? It has nothing to do with temperature. It's always the same temperature.
marble atoms being in their bouncy state. Such a number of possibilities is typically denoted with an omega.
Right, and who cares? All of this is irrelevant. It's 70 degrees, 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 it's 70 degrees. Who cares about this shit? Who cares what atom is exactly doing the movement at any one particular time? Who cares? What does it matter? How could it be interesting?
For the right part of the grid, there is only one possibility. Every marble atom is in its non-bouncy state. There are no possible variations. Now, if we take out one unit of energy from the left part, the number of possible arrangements in this part is reduced. If we compare the previous number of possibilities, omega E plus 1, where the E plus 1 indicates that it had one additional unit of energy compared to the current state, if we compare this with the current number of possibilities, omega E, we find that in the number of possibilities we have lost a factor of 1.47. But now, if we add this unit of energy to the right part of the grid and compare the previous number of possibilities, omega E minus 1, to the current number of possibilities, omega E.
So again, irrelevant to energy. It just doesn't mean anything. That's not how energy works. You don't get to say what's its density and somehow it's less dense, therefore it's less energy. It doesn't work that way. Yeah, there's fewer possibilities because you don't have enough elements to create more possibilities. You have 1 pixel. How many drawings can I make with 1 pixel? Yeah, I can't make very many. Yeah, shit. I mean, this is not the subject of temperature.
In this part, we find that the number of possibilities has increased by a factor of 30. Before, all atoms were in their ground state.
Far short of the 2 million you lost over here. So 1 unit of energy was worth 2 million possibilities on this side, and that's only worth 30 possibilities on that side. Yes, that's very interesting. No, it isn't.
And now with this 1 unit of energy, only one, but any one of the 30 atoms can be in the bouncy state. That's why there are 30 possibilities now. Overall, by
Limo at your service.
I mean, it's like arguing that, you can paint more detail with more colors or something. I mean, it just doesn't make any sense. Yeah, of course you can do more if you don't have just black and white pixels. And if you have black and white pixels and you only have 4 pixels to work with, you can't make much of a drawing. I mean, this is just so stupid. It's just so depressing. Right, should be back.
transferring 1 unit of energy, we lost a factor of 1.47 in the left part, but we increased the number of possibilities by a factor of 30 in the right part. The overall number of possibilities is the product of the number of possibilities of both parts. And this number was increased when we transferred the unit of energy to the right, which means that by transferring this unit of energy, overall we came to a more likely state. A randomly evolving system would have therefore also been likely to evolve in.
So all of this means nothing. There's a net amount of heat. It's going to move from a place where there's more motion to a place where there's less motion. I mean, this is... what is all this crap about?
This direction. Now let's check what happens if we transfer another unit of energy, and let's keep track of these factors by which the number of possibilities change in graphs. To treat both grid parts equally, I chose to plot the ratio between omega e plus 1 and omega e in both cases. So that's the change in the number of possibilities if we added a unit of energy to the left or right part of the grid. For completeness, I now also show omega e plus 1 and e minus 1 as numbers for both grid parts. So for the left part,
So look, we went up to 435 when you have 2. I guess that's what the number's going to be. And then it'll go up to like 5,000 and something, and then it'll go like 953,000, and yeah. So what?
is this factor that we're keeping track of in the graph. And for the right part, it is this factor here. Okay, now if we take out another unit of energy from the left part, the number of possibilities is again reduced. This time we lost a factor of 1.64. But if we add this unit of energy to the right part, the number of possibilities is again increased, this time by a factor of 14.5. So overall, we again increased the number of possibilities. We gained more on the right.
I don't even understand how he's talking about this being more possibilities when his number is 1,251,677. I mean, it's a billion fewer possibilities. It's pretty substantial. This is just such a waste of time.
Compared to what we lost on the left. But surely this can't go on forever. At some point, energy has to stop moving predominantly.
So this isn't about energy moving. No energy moves this way. This isn't about anything real. This isn't physics. This is some sort of crap about flipping coins.
Predominantly to the right. Let's bring the grid parts into contact so that energy can move freely, randomly between both grids, and let's see what happens.
Well, we know what's going to happen. Obviously, energy, velocity, pressure moves from high to low. I don't even know what this is. It's taking forever. Why is it so slow? Oh.
As you can see, energy continues to flow predominantly to the right until these two factors are roughly the same, until adding a unit of energy changes the number of possibilities by the same factor in both parts, until the temperatures are the same in both parts. Temperature tells us how much the...
So again, it's just... Obviously, that was the only part of the... You're going from a temperature to zero temperature. Yeah, it's going to be pretty obvious.
Number of possibilities changes if we add or remove energy. And by that, it tells us in which direction energy tends to flow.
We know which direction it's going to flow. So again, it's just such a pile of crap. Obviously, it's going to go to the side that has more velocity. It's always going to go where there's less momentum, less pressure. Always.
Energy is most likely to go where it can increase the number of possibilities most effectively.
No, I mean, again,
it's
such a distortion. Oh, it's going because of possibilities. No, it doesn't know anything about possibilities. It doesn't know any of that crap. It's going where it can go, where it doesn't get rejected, where it doesn't hit something that pushes it the opposite way. It goes where it can push. It doesn't go where it's getting pushed. It's a push-averse. The pushers win. Whoever has the most push wins. That's how the universe works. Oh, damn it.
likeliest thing to happen, and energy stops to predominantly flow in one direction if it changes the number of possibilities.
No, it's not about the number of possibilities. It's about the probability of it getting hit in the face, getting pushed backwards.
By the same factor, no matter where it goes. And that's what it means for two objects to have the same temperature.
Mikey Sherrill,
Just the evil slop. Oh, this got to be, what, the 7th commercial? I mean, I didn't have high expectations for this video, but damn. This is so bad. This isn't physics. This isn't science. This is some social engineering subject. Oh, the little elemental electrons are trying to balance a probability equation. No, they're not.
Now, this has probably been a lot to take in already, and I guess it would be...
It's wooey mush, doesn't have anything to do with the facts. Fact. Push a verse.
good to pause the video for a minute to let that all sink in.
Oh, fuck.
But there's one last thing that we need to address. I think this factor in the number of possibilities that we have worked with so far is the best quantity to look at if you want to fundamentally understand how temperature works.
It's just dissipated motion. It's shared motion. You can understand something's going really fast, the cue ball. It's going to hit a bunch of other balls. When it hits the other balls, they're not going to go as fast as the cue ball was going. The cue ball's momentum, its velocity, is going to be shared across those. And some are going to go fast and some are going to go slow. But when you add it all up, it's just going to equal the momentum you started with, the mass and velocity. So when you add up the masses and the velocity of all the balls moving, they're going to equal the mv of the ball that started it. And that's how heat works. It dissipates in the same way. Variances in velocities and all kinds of different motions and all kinds of different directions at different velocities. Something that gets a little motion sideways, tangential motion will be weaker than straightforward motion. I mean, that's how heat dissipates. This is just bullshit.
Unfortunately, it's not directly the temperature metric that the scientific community has settled on.
Yo, brother. The buttholes have settled on. The wishy-washy mush purveyors have settled on. The douchebags of physics have settled on.
It's not the metric that would lead to the equally spaced lines on a thermometer that we are all used to. You have to see that historically, temperature was not devised.
Oh, come on. I mean, there's nothing wrong with the scales on a thermometer, so the equally spaced lines is perfectly rational way of measuring temperature, and it's perfectly coherent to the facts. The net temperature. You can't stick the thermometer in each electron in its butthole. You can't do that. So you have to measure the average temperature, the average momentum.
In a bottom-up approach, starting from an atom and then figuring out how a few of them
You ought to start with the actual things that the universe is made out of, which is electrons and protons.
interact. Instead, people looked at large systems, volumes of gases or liquids, and observed their behavior. And unfortunately, the reasonable choice for a temperature metric in this macroscopic approach is not necessarily the most straightforward choice from a microscopic perspective.
The idea is if you use some kind of consistent material like steel or something else, you'll see real data points that you can collect about how fast the temperature moves through it. And, it's not that complicated.
Which means that there are, let's say, a few mathematical complications between this factor in the number of possibilities that we have.
All right, so the possibilities have nothing to do with anything. It's just a fucking mush. Oh, damn.
Stumbled on in our microscopic model and the temperature metric that we are all used to. We have to do some formula reshuffling to figure out how the two are related.
MV equals MV, and MV equals F, and MV equals weight, and MV equals pressure, and MV equals heat, and MV equals anything else you want to call energy. Yeah, it's all the same thing. It's just masses moving, period.
This is the definition of temperature, or rather the inverse temperature, 1 over T, that you can find in a lot of textbooks. That's the one that leads to the equally spaced lines on your thermometer. 1 over T is defined as the derivative of the entropy S with respect.
So we know this is the garbage entropy equation. This is not a temperature equation. This is an entropy equation about the probabilities of mixing something. This is a mixing equation. It's not temperature. Temperature isn't mixing. Temperature is moving. And it's moving directly from high to low. It's not random. It's not chaos. Ugh. This is not a real scientific formula. This word entropy has no unit.
To the energy E. Now, entropy is an interesting topic on its own. And
it's meaningless to temperature in this case. The only thing entropy means is dispersal in terms of temperature, our energy we use. It's just the fact that we can use energy that's in big clumps moving straight lines. We have a harder time using energy that's in little tiny things moving in all directions. That's not very useful, unless we put it in bomb.
You can learn more about it in one of my other videos.
Oh, fuck
All we
that.
need to know here is that it's a metric for the number of possibilities.
And it has nothing to do with the migration of temperature in the universe. The number of possibilities has absolutely nothing to do with why heat moves.
More precisely, entropy is the logarithm of the number of possibilities. We will make use of that in a minute.
I just don't even want to watch the rest of this. This is a fake subject. This has nothing to do with the temperature of the universe. It has nothing to do with any of that. This has to do with mixing paint. This does not have anything to do with temperature. It has to do with mixing things.
Now let's say this curve represents the entropy S as a function of the energy. Then this derivative is the slope of the tangent line for any given point, which tells us how much the entropy is changing with respect to the energy of the system.
So we know the energy of the system can't change. So again, more bullshit. We know from the big system. So if you're just going to watch it dissipate into the universe, or dissipate into the atmosphere, or dissipate into a tank of water, the rules dictating how the energy is going to dissipate are not intraplanetic. Alright, I have to pause. I hate this planet.
Microscopic model, however, we have been looking at a discrete system. We worked with discrete units of energy. A derivative doesn't...
Oh, bullshit. You didn't work with anything called a real concept of velocity, pressure, heat.
Makes sense for a discrete system, but we can calculate the equivalent slope by dividing delta S from one step to the next by delta E. Delta S is the difference between the entropy of one point and the next. And if delta E is just one unit of energy, we can further simplify the equation. And now we can use this formula from before. Entropy is the logarithm of the number of possibilities omega. We can plug that in.
Yeah, again, this just has to do with mixing colors. I mix 3 colors, I get a gigantic number. I mix 2 colors, I get a smaller number. I mean, this doesn't mean a damn fucking thing.
And finally, we can use logarithm rules to come to this form. And as you can see, temperature is indeed not directly this factor omega e plus 1 divided by omega e, rather a logarithmic variant of this factor. But don't worry about
all that is crap. The momentum is explicit, okay, and the temperature, the scale can read the explicit average temperature. It's just bullshit to say it's dependent on some logarithm, that you have to do some complex math because there's some complex variable. There's no complex variable.
this too much. I think going through the formulas was important to give you the full picture, but for our intuition, this
didn't have anything to do with the subject of heat, temperature, and its movement in the universe. It had nothing to do with that subject.
Doesn't really change a lot. Temperature still quantifies how much the number of possibilities changes.
Lie again. It has nothing to do with any probabilities or changes. It's as you showed in the simulation, the amount of energy, the temperature, was always the same until you increased the amount of atoms and therefore lowered the temperature by half.
If we add or remove energy, introducing this logarithm makes it a slightly different metric, but one that is still fundamentally measuring the same thing, a change in the number of possibilities.
So it's nothing to do with possibilities.
Also note this 1/over relation, which unfortunately means that we have to flip everything in our head. A high temperature actually means that there's a small change in the number of possibilities, and vice versa. Here in the beginning of the simulation, for example, in the high temperature part of the grid, the number of possibilities is changed by a small factor if we add or remove energy. In the low
Again, I don't understand what he's saying about the small factor when he went from 5 billion to 3 billion, but whatever.
Temperature part, on the other hand, the number of possibilities is changed by a large factor. So that's what this 1/over part in the formula does. Anyway, at the end of this video, I would like to close the loop from this very abstract model.
Yeah, this nonsense. Why don't you analogize it to something more real? Something that actually happens, like a boulder falling down a mountain, and how it turns into a bunch of little rubble.
Where it was easy to count the number of possibilities, back to this model closer to reality, the simulation of argon atoms. Of course, it is hard to count the number of possibilities here.
And the number of possibilities have nothing to do with the temperature. Nothing.
All the different combinations of positions the atoms could have, all the different velocities the atoms could have. But we can still apply the same logic. In the current situation...
What logic? There's no logic to this. There's absolutely no fucking distinction. There's a certain number of energy units in there, and that's what the temperature will always tell you, is how many energy units are in there. Fuck you. This is such bullshit. God,
due to the attractive force...
Physicists are just so full of shit.
Forces between the atoms and the lack of energy, the atoms are confined to stay close to each other. If we added energy, we could overcome some of the bonds between the atoms, which...
Right, because you're going to increase the velocity. So now that it's going to be possible for two things that are going fast to hit each other, to hit one other ball. So I could have the circumstance in a pool game where two balls are going to collide, and they're going to collide right where a third ball is. And they're going to end up increasing its velocity higher than either one of the two that we're hitting. So you're going to have the possibility of creating higher and higher velocities.
Would allow them to explore more of the accessible space. Therefore, adding energy would drastically increase the number of possibilities the system could be in, which means that it
won't drastically increase the temperature. It won't drastically increase anything that could matter to a rational human being.
a low temperature. Here, on the other hand, there is enough energy so that the atoms can fly all over the place anyway. If we added more energy, the number of possibilities wouldn't change that much anymore. A small change in the number of possibilities means that
in this example, there's all this extra space that everything is flying through. So how could you say there's less possibilities when there's, you know, 1,000,000 times more positions for the object to be in? I mean, your example is silly. The little ball has very few positions. This has gigantic number of positions. It's too silly.
this is a high temperature. If we brought two such systems into contact, energy would be likely to flow.
So we know if it's in that other state, you have to show me the container. You have to show me what you've contained it by, because all that stuff's going to keep dissipating. It's not going to keep flying into itself. It's just more bullshit.
From the hot system on the left to the cold system on the right.
The system on the right's going to get, on the left is going to get damn cold damn fast.
Because that is where the energy can increase the number of possibilities more effectively. The energy transfer to the cold system leads to more possibilities overall, and more possibility.
If you have the same motion in more space, it's colder.
Means that it's more likely, and likely things simply tend to happen. And that is how temperature gives the flow of energy a direction.
So it's just nonsense. Pressure creates the direction. Velocity and pushing creates the direction. Whoever's got more push wins. It's tug of war. It's collisions, frankly. Whoever has the most momentum wins.
Hey there, I'm Tobias, by the way, and I hope you enjoyed this video.
No, I hated it. Profoundly hated it.
If you have any questions about temperature or whatever, just let me know.
Oh yeah, why? Why would I ask you? Because you seem incredibly clueless, frankly. You have no clue whatsoever. You didn't say the word electron anywhere in the video or proton. Nothing.
In the comments, and I will try to answer as many of your questions as possible.
Oh, brother, I'm a preacher, I'll give you a sermon from my Bible.
Also, thanks a lot to my patrons who support.
Yeah, just fuck all those people in the ass. Why don't you just throw the money at the Catholic Church? Throwing it at a scientist isn't any better.
This video. I just started to make videos. This is my 5th video, and already having a few people who are willing to support my channel even financially is amazing to me. Thank you so much.
But you had to have 600 commercials in spite of it. Okay. Yeah. Okay. What a pile of shit. I sell science. You're a fucking pimp.
Want to support free scientific content like this?
Oh, free! Yeah, it was a long short of free, fucker.
You can find all the information in the description below. Thank you so much, and have a great time.
Fuck you, fuck you, fuck you, fuck you.
Are you guys here for the halftime?
God, I hate this planet. Alright. Well, I didn't have my aneurysm didn't explode. so at least I'll be here for another day, maybe. But this is just so depressing. Every fucking physicist is a loop-de-doo fucking kook.